All right, we're going to take a look at trigonometric proof, right? First of all, we definitely need to be familiar with our formula sheet. There are a lot of trigonometric identities that they've given us. So these can be really, really huge clues, right? The first series of 3, sine square a plus cosine square a equal 1, and their variants, very, very important to take note of these 3, particularly the first one, because usually for me, I just remember the first one, right? Just the first one here, right? Sine square a plus cosine square a equal to equal 1. Okay, so this is the first one that I remember. Okay, the next series are the double angles. The double angles are really, really important as well. Take note of what you refer to formula sheet. The formula sheet will tell us the clues, especially for cosine 2a, because there are 3 versions of it. So we need to be very, very familiar with where to find our formula, right? So that's also important. And also increasingly, I think trending is the addition formula, right? The addition formulas where, incidentally, the addition formula is the more general version of the double angle formula, right? So so do take note of these 3, particularly the first 2 groups. I think those are the bare minimum to really, really know that they're there for us, right? And then you know where to find them, okay? Next, because this is what you see on the list, what you need to really remember are those not on the list, which are these, if I can, there you go. Not included from the sheet that we need to know very, very well are the ratios of our special angles, namely sine, cosine, tangent. We just need to know these 3, sine, cosine, tangent, and then to recall the 1/overs, which are secant, which would be 1 over cosine, cosecant, which is 1 over sine, right? And we need to know the 90-degree one, the angles in degrees, and also in radians as well. So we need to be clear with our radian measure, where pi radian would equal to 180 degrees. I think I'll probably just type it in here, where we just take note that pi radian should equal to 180 degrees. So if we're converting radian to degree and vice versa, this is the one thing that I use all the time to remember, right? And also, the other thing I mentioned was the 1/overs, right? So if we see the 1/overs, take note that the 1 over sine, 1 over sine a would actually equal to cosecant a. And 1 over cosine a would equal to secant a. Right? So these are things that we need to be familiar with as well. All right, now moving on to, moving on to the next one. Okay, so I'm going to clear this. So how do you do about how do you go about doing the proofs, right? So one of the guidelines that we can use is go from complex to simple, right? So for example, we have a question here, prove the identity of 1 minus x equal over 1 plus x equal to secant x minus tangent x bracket square. So what do you mean by complex or simple? So, the ones that we're more familiar with arguably would be sine, cosine, tangent. So these are slightly more familiar, particularly sine and cosine. They're the more ratios that we're more familiar with because we've seen them for about 4 years, right? But secant, tangent are slightly different. We've just seen them in over 2 years. So in this case, what we can do is to start from the right-hand side. It is possible to start from right-hand side. So the working process goes right-hand side equals to what have they given us on the right-hand side, right? And we go on to the next line. So this is where we try to make it simple, where we're expressing what we see in terms of sine and cosine, So that's where we're going with it, yeah? So we turned secant to what we said earlier. Secant was 1 over cosine, so we turn that into 1 over cosine minus sine over cosine, and we closing bracket square that. Next, what we're going to do is slightly interesting. We're going to bracket we're going to take these as a single fraction. We're going to take this as a single fraction, combine it as a single fraction because they have a common denominator of cosine x. So we take a single fraction with the brackets and square that. All right, so don't square it yet. Just simplify the bracket first as a single fraction. Then we go square the numerator and the denominator. So this is where magic begins to happen. And this is also where, we see some of our friends get confused when it comes to this stage, because we're going to prove something to the left-hand side. So we're getting somewhere where it's supposed to get more and more closer to 1 minus x and 1 minus sine x and 1 plus sine x. So what do we do from here? This is the critical part. We notice that the numerator kind of already has a 1 minus sine x, but the denominator is in cosine square. So what do we do to make a cosine something turn into in terms of sine? So this is where our identities come into play really, really importantly. So we're actually turning cosine square x into 1 minus sine square x, right? 1 minus sine square x. Let me back up a little bit, right? So we're using the identity of sine square x plus cosine square x equal 1. So we're using this identity. Oh yeah, so this is where, because I'm using Zoom, so yeah, okay. Plus cosine square x, this was our identity that we saw earlier. Right, this was identity equal 1. So because of that, we make cosine square x the subject, so we turn cosine square x into 1 minus sine square x. So that's where it came from, right? So this leads us to factorizing 1 minus sine square x, because 1 is a square number and sine square is also a square number. Sine square x is also a square number. So we turn that using our a minus b. So this is using our algebraic identity, right? This is I call it our third friend. So a square minus b square, factorized into a minus b bracket a plus b. So in this case, 1 minus sine square x will factorize into 1 minus sine x bracket 1 plus sine x. Then we begin to see the magic, because numerator and denominator has in common a 1 minus sine square x. So what we can do literally is to cancel off 1 minus sine square x, 1 minus sine x, and cancel off from numerator, and cancel off 1 minus sine x from the denominator. So this will lead us into 1 minus x over 1 plus sine x. And this will lead to our left-hand side. Oh, that was massively embarrassing. This really should be written as left-hand side. Sorry about that, guys. This should equal to left-hand side, and then we prove it, right? So that's our first case scenario, okay? Let's go on to the next case. Right, okay. Okay, let's go on to the next case. Okay. So next case, again, so here we have cosecant x, cosecant theta, cotangent theta, prove that it is equal to cosine cubed theta over sine squared theta plus cosine theta. So how are we going to prove that? So earlier we did right-hand side equal left-hand side. Just in case we're wondering, we can also start from the left-hand side. Right? There's nothing to say that we cannot start from the left-hand side. And in this case, we're starting from the left-hand side because we're sticking to the principle of turning the more complex unfamiliar trig into the more familiar trig, which is in terms of the simpler ones would be in terms of sine and cosine. So we start with left-hand side, cosecant x, tangent x, cosecant x, cotangent x, right? So we turn cosecant x, cosecant theta into 1 over sine theta, and then we turn cotangent theta into cosine theta over sine theta. How does that work? Because we need to remember, and it's also not in formula sheet, that tangent theta is actually equal to sine theta over cosine theta, right? So we start with that. The next step is we're going to multiply numerator and denominator. Numerator to numerator, so 1 times cosine x gives me cosine, 1 times cosine theta gives me cosine theta. Sine theta times sine theta gives me sine squared theta. Next, we're going to do something really, really tricky here because we notice that, let me back up a bit. We notice that we have our cosine in place already as the numerator. We notice that we have sine squared kind of in place as the denominator already. So what we're going to do, what we do now is quite elegant, and sometimes people say really tricky, is we multiply the numerator by our very good friend sine squared theta plus cosine theta, right? Because sine theta plus cosine theta is actually still equal to 1. It's still equal to 1, right? So we do that. So why on earth do we do that? Well, the next stage explains it. We're going to expand it into cosine cubed theta plus cosine square, let me read again. Cosine theta multiplied by cosine squared theta plus sine squared theta becomes cosine cubed theta plus cosine theta sine theta. And all of this is divided over sine squared theta. Right? All of that divided by sine squared theta. Then what we're going to do, we're going to split the fraction. So earlier we combined the fraction, now we split the fraction into cosine, oh, this was not so good. This was cosine cubed theta over sine squared theta plus sine, oh, what are we doing here? Oh, this was cosine cubed theta. Okay, hang on. What did we do here? Yeah, cosine cubed theta over sine squared theta plus, this is massively not accurate. Let me rewrite this. So it's not this at all. So this has got to be, so this is incorrect. Let me white it out. This one's totally incorrect here. So we're going to rewrite it as the second fraction would read cosine theta. I'm just using a horrible version of theta today. Plus, no, cosine theta sine squared theta over sine squared theta. Okay, that's what it should look like. Apologies, guys. And, oh, what did I do here? So I massively okay. And then this should equal, so I'm just going an in-between step here. And then this shows cosine, so this will actually equal to cosine cubed theta over sine squared theta. Right, and this was in bracket. And then this will read plus cosine theta, because sine squared theta and sine theta cancel. Right, so these two eventually have canceled. Right, this was numerator, this was denominator. These two cancel. Right, so that's how we end up as proving equal to right hand side. Okay, next. Okay, and at times we can also go simple to complex. So this is where it gets really interesting, right? So why? So here we're proving sine 2a it should equal to 2 tangent a 1 plus tangent square a. So some of us might be tempted to start from tangent. Well, to me, we could do tangent that will go to sine 2. This is where it can potentially get dangerous. So the 2 remains outside. If we did right hand side first, 2 remains outside. Tangent, as we said earlier, will turn into sine over cosine a, right? Sine a over cosine a. So we have numerator, denominator, the numerator as a fraction. then in the denominator, we would also have to do something to, and we're not so sure. We might be tempted to turn into sine square over cosine square. So we might be tempted to turn tangent square A into sine square A over cosine square A. It's not impossible. It's just that it will be another layer. The denominator would also become a fraction. So that can be potentially tricky. So here's an alternative. We could go simple to complex. Here, we can indeed start from LHS. Let's see. LHS equal to, left-hand side equals to sine 2A. We turn sine 2A using our identity double angle into 2 sine A cosine A. And then what we do is our good friend, we take 2 sine A cosine A and divide by sine square A plus cosine square A. Why on earth do we do that? Because sine square A plus cosine square A equal to 1. Again, right? Then what we do is we going to, what are we doing here? Yes, what we're doing here is we're, oh, this is interesting. Oh, yes. So what we're doing here is we're dividing the numerator. So we're still having a fraction over a fraction, okay? So for the numerator, we divide by cosine square A. For the denominator, we'll divide the denominator also by cosine square A. So this is where it gets a little bit hairy, but bear with us, okay? So 2 sine A cosine A divided by cosine square A. What does it become? It actually becomes 2 sine A over cosine A, right? And in the denominator side, sine square A divided by cosine square A gives me tangent square A. And cosine square A divided by cosine square A gives me 1. So what I've done is subtly going to create, what we've done is we created the denominator as a version of 1 plus tangent square A already, right? In our final step, we have to appreciate that sine A over cosine A would actually become tangent A. So that's how we get equal to 2 tangent A over 1 plus tangent square A, and that proves 2. That gives us to the right-hand side, and that's proven. Okay, so I hope these few examples give some insight into how we can prepare for our trigonometric identity. Of course, as for this topic particularly, practice is really, really important. The more we practice, the more versions we see, the more we get experience and confidence into when to turn complex to simple, when to turn simple to complex, and also to notice how useful we can access the identities that the formula sheet already given us. And also to appreciate sometimes, here I didn't mention, but sometimes you can have the examples that include the angle with 90 degree, the angle either 90 degree minus theta or 180 minus theta. Those versions, we can also need to appreciate that as well. However, if we're a little confused, we can still use addition formula to expand, right? If we're doing, let's say, for example, cosine bracket 90 minus A, and we're not sure what to do with it, we can actually use addition formula, put the first angle as the first angle, 90 degree, and put A as the second angle, right? So you can do something like that, right? In the meantime, you can also practice, try out this question to prove cosecant 2x minus cotangent 2x is equivalent to tangent x, right? So you can try a question like this, and if you're confused, you can also feel free to reach out, yeah? All right, so that's what we have for today. Thank you, and good luck.